What specific problem do BD3LMs aim to solve in the context of discrete diffusion models, and how does it relate to existing limitations in autoregressive models?
BD3LMs aim to address three specific limitations of discrete diffusion models: the inability to generate output sequences of arbitrary length, inefficiency in inference due to the lack of KV caching, and inferior quality as measured by perplexity compared to autoregressive models. By introducing a block diffusion approach, BD3LMs allow for variable length generation and leverage autoregressive modeling over blocks of tokens, which enhances efficiency through KV caching. Additionally, BD3LMs tackle the high variance of gradients during training, which has been a significant factor in the performance gap between diffusion and autoregressive models. The proposed custom noise processes in BD3LMs help minimize this gradient variance, thereby improving the overall quality of generated outputs. Ultimately, BD3LMs interpolate between the strengths of autoregressive and diffusion models, making progress towards closing the perplexity gap and enhancing the applicability of discrete diffusion models.
How does the proposed block discrete denoising diffusion language model, BD3LM, work? Please illustrate the methodology step by step, including its unique components.
The block discrete denoising diffusion language model, BD3LM, operates by combining autoregressive modeling with discrete diffusion processes to generate sequences of tokens. First, it organizes tokens into blocks of a specified length, allowing the model to define an autoregressive distribution over these blocks while performing diffusion within each block. The methodology involves a two-step training process. Initially, a forward pass computes keys and values for the entire sequence, and a second pass generates denoised predictions for all blocks simultaneously, leveraging a transformer architecture with a block causal attention mask for efficient computation. To address high gradient variance, BD3LM employs custom noise schedules that minimize this variance during training, which is crucial for improving performance and closing the perplexity gap with autoregressive models. Finally, during sampling, BD3LM generates one block at a time, conditioned on previously generated blocks, enabling the model to produce sequences of arbitrary length while maintaining coherence and quality.
Can you provide a simple and illustrative example demonstrating the inner workings of BD3LMs during the token generation process? Walk through the main steps of the algorithm using this example.
To illustrate the inner workings of block discrete denoising diffusion language models, BD3LMs, during token generation, consider a scenario where we want to generate a sequence of text. First, the input sequence is divided into blocks of tokens, say a block size of 60 tokens. During the generation process, BD3LMs sequentially generate one block at a time, conditioning on previously generated blocks. For each block, the model applies a diffusion process to predict the clean tokens from their noisy counterparts, leveraging a neural network that outputs probabilities for each token in the block. The algorithm begins with a forward pass where keys and values for the entire sequence are pre-computed, allowing for efficient KV caching. Then, in a second forward pass, the model generates denoised predictions for the current block based on the noisy input and the clean tokens from preceding blocks. This process continues until an end-of-sequence token is generated or the desired sequence length is reached. By utilizing this blockwise approach, BD3LMs can generate sequences of arbitrary length while maintaining high sample quality and coherence, effectively overcoming the limitations of traditional autoregressive models.
What are the theoretical or practical advantages of BD3LMs over traditional autoregressive models and other forms of diffusion models?
BD3LMs offer several theoretical and practical advantages over traditional autoregressive models and other diffusion models. Firstly, they support variable length sequence generation, allowing for outputs that exceed the fixed length constraints of previous models, which is particularly beneficial in applications like chat systems. Secondly, BD3LMs improve inference efficiency by utilizing key-value (KV) caching, enabling faster generation through parallel sampling within blocks, unlike autoregressive models that generate tokens sequentially. Additionally, BD3LMs achieve state-of-the-art perplexity scores among discrete diffusion models, closing the performance gap with autoregressive models by addressing high gradient variance through custom noise processes. Finally, the integration of autoregressive modeling over blocks of tokens with diffusion processes enhances the quality of generated outputs, making BD3LMs a more robust choice for language modeling tasks.
How did you validate the effectiveness of BD3LMs? Describe the experimental setup, datasets used, and the metrics measured to demonstrate performance.
To validate the effectiveness of block-discrete denoising diffusion language models, BD3LMs, we conducted evaluations across standard language modeling benchmarks, specifically using the 1 billion words dataset LM1B and Open Web Text OWT. The BD3LMs were pre-trained using the maximum block size for 850K gradient steps and fine-tuned for 150K gradient steps, with a focus on adaptively learning masking rates to reduce training variance. We measured performance using perplexity as the primary metric, comparing BD3LMs against prior diffusion methods and autoregressive models. Results showed that BD3LMs achieved up to a 13% improvement in perplexity on LM1B and outperformed all prior diffusion methods, demonstrating superior generative capabilities and the ability to generate sequences of arbitrary lengths. Additionally, we assessed zero-shot generalization to unseen datasets, where BD3LMs achieved the best perplexity on several benchmarks, further confirming their effectiveness.
What specific results were reported in the paper regarding the performance of BD3LMs, particularly in terms of perplexity and generation capabilities?
The paper reports that block-discrete denoising diffusion language models, BD3LMs, achieve new state-of-the-art perplexities among discrete diffusion models, outperforming prior diffusion methods by up to 13% in perplexity on the LM1B dataset. Additionally, BD3LMs demonstrate the ability to generate sequences of arbitrary length, significantly exceeding the training context length of 1024 tokens, which is a limitation for many existing diffusion models. In terms of sample quality, BD3LMs produce sequences with higher coherence compared to samples from other models like MDLM, approaching the quality of autoregressive models. Furthermore, the BD3LMs exhibit improved generative perplexity using an order of magnitude fewer generation steps compared to alternative methods, showcasing their efficiency in both perplexity and generation capabilities. Overall, the results establish BD3LMs as a significant advancement in the field of language modeling.